Hello everyone, we are Ekin, Tolgay and Semih. Our project is designing an automated storage and retrieval system robot that can work in warehouses, distribution centers to automate the operations. Global e-commerce volumes are expected to grow 100% from 2018 to 2022 in the United States of America. This rapid increase of e-commerce shares in retail sales, combined with customer expectations of quicker and more flexible deliveries, is putting more pressure on the retailers to design a more efficient supply chain network. To handle the increasing customer demand, traditional warehouses need to improve the human power, and the crowded work environment leads safety issues. Thus, autonomous systems need to be adapted to warehouses to make the operations more efficient, safer, and cost-effective. In this project, the objective is to construct an ASRS robot that can move between shelves with high maneuvering capability, pick and place items from shelves with a 3 degree of freedom robotic arm, and a vacuum grabbing mechanism that is located at the end effector. Therefore, it is expected and designed to increase storage capacity while decreasing the manpower needs. The robot contains approximately 110 parts including the joints and the links to 3D printed robotic arm, sheet metal frames to mount the PLC, drivers and other electronic components, driving wheels, batteries, omni-roll wheels which can change the center of rotation and increase the maneuver capability, suction cups at the end of the effector of the robotic arm, and the shaft that connects the frame and the front wheel system. The assembly of the robot can be separated into three main parts, which are robotic arm, driving system, and the frame with electronic components. Thus, the assembly and the test of these major parts can be done separately, which gives us setup flexibility. Since the robot contains different moving parts, the rotation of the robotic arm links are done by 12 volts of stepper motors with reducer. The steering and driving are done by 24 volts of 3000 RPM DC motors and their reducer. The motion controller is selected as Siemens PLC and the pulse and direction signals directed to the robotic arm stepper motors. For the manufacturing part, we wanted to work with different types of materials and manufacturing technique, so we used plastic and metal parts. For plastic parts, thankfully we had two 3D printers that we can operate non-stop, and we used PLA and TPU as raw material. We printed out our robotic arm links and joints from PLA, and we used high infill while printing them so that they were stable and strong, but relatively lighter compared to metal parts. However, for cover parts, we used low infill so that they were light, and since they don't carry any load, it fitted our needs. We used TPU material to print out rollers as shown in the image because they gave better results than PLA rollers because of their high friction. For metals, we used a couple of different techniques including sheet metal laser cut and bending methods, and also turning and machining methods. We use sheet metal for our chassis parts so that they are easily manufactured. However, for our shafts, which are for motor, drive wheels, and only rolls, we use turning and machining to have appropriate cuts. We mainly design for metal parts to carry our major loads. When gripping with a vacuum mechanism, initiating the vacuum requires an almost perfect contact of the suction cups to the box. So our printed robot arm has three joints in the same plane to maintain this parallelity between the end effector and the suction surface of the box. And another critical calculation for the robot arm is to maintain the motion axis of the box, which can be tracked through the first figure as dashed red line. If this axis drifts away too much from its original course, it could lead to a leakage in vacuum, which will completely stop the vacuum. Using this condition, the mathematical model can be restricted. With inverse kinematics, we can derive equations for the second and third joint angle in terms of the first one. Since we have only one axis of motion, the position can be expressed in terms of the first joint. Thus, this design of gripper and robot arm enables to pick boxes between 20 by 20 and 40 by 40 centimeters with a height more than 20 centimeters. All of this calculation is done through MATLAB and transferred to a function block in PLC. For our test and commissioning, we first tested our driving motors and wheels while they are not on board. However, due to manufacturing and assembly defects and errors, the linear velocity of our driving wheels was not perfectly matched. So we tested and adjusted their speed using an offset value and a tachometer. Then we tested our theoretical robotic arm positions and angular velocities with real-life values and see if they match and make some adjustments to control the robotic motion more precisely. After the testing without load is done, We put our robot to the ground and tested the motion and kinematics. Then we made a rehearsal for robot to go to a specified position and reach the desired goal point on the shaft. In the next steps of the project, front wheel steering action can be done by an additional DC motor, thus the front wheels can rotate 180 degrees and steering could be done by rotation instead of speed change. The robot can be equipped with LiDAR sensor and a camera to detect and avoid from obstacles such as forklifts, workers. Thus, the robot can be easily adapted to industrial applications. Finally, to work at different height cases, the robot can be equipped with a pinion on its front wheels, and the racks can be put on the shelves. Therefore, by using a rack and pinion mechanism, the robot can work at any height.